Right. Okay. No. Okay. Sorry. By the way, that was just we're recording the session, so I can obviously send you a video of our session. Okay. I just clicked that. Okay. So I'm just checking through my email here.
I'm trying to find. I'm on the UCAS. Is it profile? No. Oh, this UCAS hub's confusing. Aha, here it is.
Good.
Test statement. Okay. Nice. So do you want me to just copy and paste all the words?
Yeah, that's fine. Absolutely fine. If you've got a downloadable document, that's equally just as good.
There.
Okay, great stuff.
Nice.
Thanks for that, Isaac.
No problem.
Okay. I'm just gonna refresh that page. Okay, good. There we go. I like that. Mathematics is the music of reason. Fantastic start. So is James Joseph Sylvester. Okay. Okay, good. Good. So your physicist is okay. You got physics in your A levels. Good.
Yeah.
Good stuff. Okay, good. Reading works such as pleasures of counting. Okay, good, good. That's all there. Okay, prime number conjecture. Fantastic. Okay. Fantastic. Custom distribution. Okay, machine. Okay, great stuff. Good. Right, I think it's an excellent personal statement, Isaac. Fantastic, and it's given me a glimpse of what you've been exposed to and such, which is really good, and also the fact that you've got an inkling towards the physics side of things as well. So you are also somebody who's practical in that degree. Great stuff. Okay, all right. Okay, so do you know who your interviewers are? Is this something you've done some research on?
Yes, I've got their names somewhere. Let me get them. Is it them? Oh. No. How do I set this up with Leslie? Mr. James.
Yep.
Dr. Rob Jack. Wait, this is Mr. James Dougal, Dr. Stacey Law, Dr. Rob Jack, and Professor Jim Pringle.
Okay, fantastic. And have you done a little research about them just to sort of work out what areas they're mostly specialized in?
Honestly, I have not. Do you reckon I do that?
Yes, absolutely. Because it's something worth doing, and you'll be able to find quite a lot of information on the website. So even if you just put the names into Google, and it will give you a bit of it will take you to the website where you can get a bit of an idea as to what the fields are, what the research has been in, because it can always sort of give you a flavor for perhaps what elements of your personal statement they may want to drill in more detail.
Perfect. Okay. I can do that. I can do that. That's fine.
Good stuff. Fantastic. And you got a little bit of time anyway for that, which is good. So you can kind of pace yourself accordingly. Right. Okay. So the interview process, of course, is quite daunting in the sense that you're not really quite sure what questions you may be asked, and trying to get a varied exposure is really kind of key to, and also knowing your personal statement quite in depth, because especially if you make mention of books and such, you may well be asked some questions about what you may have found fascinating in that particular book, and may have to go into some depth. Is that something that you have done a thorough research on, in terms of, do you know your personal statement material fairly well?
So I haven't read like the books in like a year, so I've literally got them here. I'm gonna go like, I'll probably just read over my favorite chapter, like, because
yes, absolutely. Read over your favorite chapter. That's definitely something that, again, I would highly recommend.
Yeah.
Okay.
I wouldn't be able. I don't think I'd be able to give my best answer if they asked me a question on it.
Yeah, and the whole thing, I think, part of what they're trying to do as well is to get you out of your comfort zone, and then see how you would apply your experiences, your knowledge in a bit of a novel situation. And I think the key thing is, of course, to try and articulate your thinking as much as you can, especially given that it will be obviously online as a process. So if they can see your thought process, it gives them a better indication of how well you can think either outside the box, or whatever it is they may be looking for in the problem that they pose to you. Okay.
Perfect. Okay.
Good stuff. All right. So just as a general, I'm going to throw some questions at you, and these are going to be sort of questions that, from my perspective, I'll be trying to assess a number of things. Okay. So just be as relaxed, because there will be feedback at the end of this session, and there'll also be, I'll try and, of course, have elements where I'll let you do some calculations and such, and just see how we get on with those as well. Okay, how does that sound?
Thank
Good
you.
stuff. Okay, all right. So then, Isaac, tell me why you want to read mathematics at Cambridge.
I think maths has just become such a part of like my personality. In a fact, I can't imagine not continuing it. And Cambridge is something. It just when I it just feels right. I don't know how, like, I don't know. It's my dad's from the area. Like, he was born in the Cambridge area, and like I've been to like the Cambridge area, and it's really nice, and I want to be down southish, and it just fits like every box. Like, I can't, and like, even like how they do the school, like, because I have a further maths class of just like 3 of us, and they have those small lecture groups, which it just works a lot. I really bounce off like just like my close. I'm a person that has a small friend group, and I bounce off people like that. So it just fits me to a T, basically.
Fantastic.
Yeah.
And is there anything particularly that you found that that attracts you most? Any one particular thing that you would probably say that is the greatest thing that attracts you to want to read maths at Cambridge?
Can I say something about, like, I think I really liked Emmanuel, like the college, loads. Like, there was someone on it who was talking, and like like, when you just like respect, like just admire someone like instant, like, yeah. And then it was, I can't remember this. I think it was a PhD student or something.
Yeah.
And I was like, so, and if that's like, if someone like that can come from a place like that, I want to be like someone like them.
So you kind of proved to be an inspiration and such to you. Okay, good stuff. Okay, well, thank you for sharing that part. Now, let's just think of a bit of a hypothetical situation. So imagine you have an aunt who really dreads mathematics. And
Yeah.
as you said, you are quite passionate, and you can't see your personality, being sort of disjointed from maths, as it were. Is there an equation or a number or anything that you might use to try and persuade her to love mathematics? And if so, what would that be?
There's always the classic one of is it e to the power of is it Euler's theorem, that e to the power of I pi minus 1 equals 0?
Okay, so what would you say to her about that number?
I'd say like,
And feel free to share the sketchboard if you wish to write anything, and
how
you'll
do I
find that under, I will help you out
how do
here.
I share it?
If you go to the button that, let me just enlarge this. So if you go to share screen, can you see a button that says share screen at the bottom?
At the bottom.
Just next to, so if you put your cursor and you're going to see where it says chat.
Oh yeah, on the Zoom.
Share screen.
This.
Correct, and then there you will, good.
Is that it?
Yeah, and there's another screen. Oh yeah, you could use that screen. That's absolutely fine. Or you could, yeah, that's absolutely fine. That will work if you wish to use that one. The other thing you could do, of course, I'm just trying to see if, there you go. Now you've got the writing too. Okay.
How do I do?
Yeah, that should work. Even though you do have the symbol.
Do I have symbols?
Yeah, just onto the left of your screen, you'll see the symbols.
Oh, nice.
Yeah, but don't worry too much. I know exactly what you mean.
Yeah, it's just awesome, isn't it? It's
Yeah.
like, it's just having something. So there's like they're like those 5 numbers, like the foundation of most maths, and to be able to fit them into one.
So,
Is
okay, for some reason I want to.
I'll just write pi.
You're right. Yeah, that's absolutely fine. There's quite a lot in there, isn't there? It looks like pi, the number pi itself.
I know. I think they've written.
Okay, we'll get there. Good.
Yeah.
Okay, fantastic. So, and feel free to use the pen. There's a pencil as well that you could use if you don't want to type.
Just type. The fact you can
Yeah.
have, like, you can have an exponential and put it to a power of, you can have a number that doesn't end, and you can put it to another number that doesn't end, and then something that we can't even, like, people can't even conceive what, like, a number that isn't even true, and then is equal to 1.
Yeah. So to her not knowing a lot of maths, you may be queried as to, well, what is the significance of that number E? What's the significance of that number pi and I? How do you go about talking about that?
Well, okay. I think first we start with pi is what been around for a while, and it's how they first measured circumferences of circles. They realized, and that if they have a diameter and you times it by number roughly about 3.14, that equals the whole length of the circle.
And why was the circle revolutionary?
Because the circle, if now we know what the circumference is, we can find the area of circles, and then we can apply that to other function of mathematics, like finding areas in graphs and stuff like, and then it turns into into trigonometry, and it's ridiculous. and then I is when you're
And I
trying to
suppose,
find
yeah, go on.
when you're trying to find two numbers that multiply, when you're trying to find a number that multiplies by itself equals -1, it can't be done, and we have to create our own number scale called called the imaginary scale, and I is it's like you base unit sort of thing, and E is if you have a curve and you want to find it, and you want a curve's gradient to be the same as its function is E, and like that also has so many applications, as you can use it as integrating factors, and like they all have such like there's such foundations for everything. Like there's like you can't even there's like infinite things you could describe about them. Yeah.
Right. And do you reckon by this stage she will have fallen in love with the subject or drawn closer to it, or might she be thinking, "Ooh, that sounds scary"?
She might be a bit overwhelmed, but I think she might be able to appreciate some of the beauty of it.
Yes, absolutely. And of course, something about pi as well, because when the will was actually made, and that itself was quite revolutionary. And of course, some of the things that you mentioned about it then coming into different arenas of application makes it quite a unique number in that sense as well. Right. Okay. Good stuff. Thank you so much for that. Okay, so we're just going to have a go at just a few questions, and of course I see that you've mentioned some aspects of physics, so we might combine some of those two and also look at some pure elements within maths itself as well. So what I'll do, I'll just take control of the screen again. Share screen. Do you want to continue? Yes. Okay. All right. Great stuff. Okay, so just something to warm us through or start us off. How would you, if you were posed with a question like this, Isaac, how do you approach it? Or have a go at solving that problem?
Okay, is that so? Would you rather me write this on paper or write on?
Yeah, you can absolutely write it on paper if you wish to, and you can. Are you able to? Okay, I take it you might not have a visualizer, which is absolutely fine. You're not expected to have one anyway. Okay, is there a way of moving your camera over your work, or is it the one on the laptop?
Okay, let me get to a new page.
So what I could do is
I'll lift it up. Is that close?
Fantastic? Absolutely. Yeah, I will definitely be able to make out what you've written on your paper. Good.
First of all, I think we need to cancel the logs, I'd probably say. But as you've got okay, I'll try putting it all to e to the power first.
Okay.
But not e. I mean, I thought it's ln. Okay. So sine x cos x to the power of a quarter. Is that? I feel like I've made some mathematical lies up here.
Okay.
Okay. I feel like you've got to use some.
So you have over there, okay, sine x to the power of a quarter times sine x to the power of a quarter equals cos x sine x. Okay, all right. And you're proceeding from there.
Yeah. But, mm, is that okay? I'm gonna put it all to the power of 4 to give sine x. Oh no, so that will go. That will cancel to sine x cos x to the power of half equals. Okay. Equals sine. Okay.
Okay, so I'm
I
just
got that.
trying to. So you've got sine x cos x equals cos squared x sine x.
And then
Okay.
I'm gonna plug in probably sine squared equals 1 minus cos squared. Just to see if and then I'm going to divide all by cos x to give sine x equals cos x minus cos. And then and I think I might have a
Solution.
no, I've got I've kind of made some oopsies, but
Okay.
I think I have a binomial expansion, but I'm not too sure. I've got okay. Something like oh no. I think so. I've got. I don't. Okay, this is what I've got to. I don't really.
Okay, so you've got, okay, something raised to the power of 6 there with your cos. Okay, now let's have a look there. All right, I see what you've got. And that is a slightly, okay, so you have taken that cos x, sine x, cos x. And how have you then simplified it? Okay, so you could have, of course, simplified it from there by, okay, I see what you've done. So you didn't divide it with sine x cos x on both sides, because that would have then given you 1 equals cos x sine x. Does that make sense?
That would have been a lot easier.
Yeah.
That was not very big brain. And then Oh, and then 1 equals cos x sine 2x, which equals half of sine 2x. So 2 equals sine 2x sine. Okay, that's why you got.
Okay, so let's see what you've done there. Okay, sine to the equals, ooh, okay, I see. So 2 equals sine 2x. Okay, so with that one, well done for making your first attempt. And there might be another way to look at it. Is there any other way that you might be able, just take another moment to again look at the problem fresh? Might you be able to think of another way to go about solving this problem?
Yeah, at the very start, I'm a bit confused because I don't, when you times two, what is there any rules for when you times two logs together? If what they
Not necessarily. There definitely is a law for. You can make a general rule if you wanted to, but we can think about it in a slightly different way because at your A level or at your stage, you would not have been introduced to any rules governing logs being times together. Yeah. So you know
I
about logs adding together,
yeah, and
not
minus.
necessarily timesing together. But we see here we've got a quarter. We've got two of these logs to the base of sine x cos x, sine x times log to the base of sine x of cos x equals a quarter.
Could you put maybe like put one side to the other, so you have one log on one side and one log on the other? So you do log sine x cos x sine x equals 1/4. That does not look nice. Could you try do something where you solve them simultaneously? Like you have, so you bring over you make one, you bring over one to the other side.
Yeah.
And then you put sine x cos x to the power of the other side equals sine x, and then you do it with the other side, and then they might cancel. They might
Exactly, and exactly which route you're looking, and that might probably even be less elegant than some of the solutions we might be able to think of here. So we've got two terms, and the product of these two terms is a quarter. Yeah, that's one way of looking at it.
Oh, so there you go. Oh,
Yeah.
no,
So we can think of what each of these terms could.
equal.
Yeah.
Yeah.
Would that be one way of possibly going about it?
Okay. So you need. Okay. So you make log. So you do sine x cos x to the power of a sine x sine cos x to the power of b cos x. A, the product of a and b equals a quarter.
Yeah.
Okay. Okay.
We could make A equals to B, can't we?
Yes, you can do it. Boom. Yes. So a equals a quarter equals 1/4 b. Plug that in. And then could you divide them?
Yeah. So just to get so did you then, is this what you have currently? And then you've made, as I was just trying to follow your thought process, did you then make log of sine, or rather sine x equals a half?
How do you know they both equal a half? Couldn't they equal like 2 and like a 16th?
Yeah, absolutely. And this is exactly what I was just trying to follow. I was just trying to follow your thought process and say, did you make them equal, or did you use different
I
parameters?
use A and B.
Oh, you just use A and B. That's fine. Okay. So you've kept on using A. So you've now got A on the side. Okay. All right. So you've got something that is that what you've got at the moment?
Yeah, and then I've got cos x equals
Okay.
sine x cos x to b, but then I've plugged in.
But then you're now using a simultaneous equation where you've said cos x equals sine x cos x to the power of
1
well, B
divided.
would be that.
Yeah.
Okay, good.
Is it a quarter B?
Is it a quarter B?
Quarter A, even, isn't it?
Quarter A, sorry. Okay.
Is it fine if you divide? So if I had the sine x equals bracket sine x cos x to the power of a, is it fine if I divide the sine x by cos x?
Yeah, okay, yeah. And so you get tan x. Okay, good.
Tan equals bracket sine x cos x 3/4 power 3/4 a.
Sine x. Yeah, okay.
And times isn't it times cos? That is sine x times cos x.
So what would you then do with this here?
Isn't that is that bracket the second bracket times cos x as well?
Times cos x, sorry. Yeah. You're absolutely right. Yeah.
And then would you? I don't really know what to do here. Maybe expand it out so you have sine x over cos x equals cos x to the power 3/4 a times sine 3/4 a x.
Yeah, okay. And then where might we go from there to try and deduce A?
Can you use some logs again?
We could use logs. Could we use logs?
Log, no, because they're in X's, aren't they? Nothing's standing out. I've got cos x to the power of minus 3/4 a minus 1 equals sine x. Oh, and I've realized I've just made a mistake as well.
Yeah.
The cos x bracket sine x cos x equals 1/4a, not 1/4 times a. So you
Yeah, it's
can't.
1/4a, correct. Yeah.
Yeah, that's annoying.
Well done for spotting that. Good.
I'm a bit unsure on what to approach next. I've got some. It's not looking very elegant.
But actually, it's not. Yeah, it's not a very straightforward one. But we'll explore this in more detail. But just for the present moment, if we had the product of A and B equaling 1/4.
Yeah.
As long as the two terms. Yeah. And we can make them equal as long as the two terms are such that we get a product of 1/4, then our solution would be justified.
Is that okay?
Absolutely.
Because x can still be anything, can't it?
Yeah. So we can work and start off with this.
That makes
the power of a half.
Easier. Oh, that makes life so much easier. And then sine x equals cos x, tan x equals 1. So x equals tan minus 1. X equals tan minus 1, 1.
Yeah, so you get x. Sorry, so you got tan x equals 1.
Yeah.
And then you therefore said x equals pi over 4. Yeah. Is that right? Because it's periodic, of course, where n can then be 0, 1, 2, so on and so forth. Of course, if we plug that in, but this would only be applicable, if you like, in the first quadrant, because that's the only area where it would get this defined. Yeah?
Yeah.
Okay, good. All right. So well done on that. So you articulated your thought, and we sort of thought of different ways. But like I say, this is not quite it's not a usual problem you see in your A-level maths paper. And generally, we don't look at sort of rules governing laws regarding multiplication of logs. But this is definitely one way you could approach it if you had two logs multiplied.
It was quite interesting. I didn't realize you could have made it equal, the A and B equal anything you wanted, because I kind of forgot the x was even.
And half just happens to make it a little bit easy, because then you can actually simplify it to something much easier to work with. Okay, good stuff. So of course you also told me that you've kind of looked at the applied element of mathematics in the sense of you doing physics as well, which is really good. And sometimes the questions can also vary. They can also look at mechanics questions, okay, especially given that you are doing physics. So let's just look at this problem here, and just give me a bit of insight as to how you would approach such a problem.
Okay, small bodies. Circular motion, isn't it?
Good.
Yeah. So it will come off the circle when the magnitude of the force outweighs the centrifugal. So it's when the is it when Newton's 2 is larger than the central not centripetal force, isn't it? That's when it.
Yeah, if you're okay, so you're kind of thinking about it as having a free body diagram, and at the point where it comes off, you obviously have, is it zero reaction? Is that what you're referring to?
Yeah.
Zero reaction force, okay, or normal force. The normal force will be zero. Yeah, absolutely correct. Good.
Okay. Just trying to remember what the acceleration, what the centripetal force equation
So
is.
that is not to worry. So the formula for that is
mv squared over r. Is that right?
correct. Yeah, absolutely spot on. So mv squared over r is one representation, or you've got m omega squared r.
Okay, and then what's with your gravity? That is your. And then your height, etc. Okay, I think I've got a solution. I will talk through it.
Yeah, thank you.
Okay, so it will the ball will come off when mv squared over r is larger than mg,
Okay.
and then so your m will cancel, and you know your radius is h over 2,
Yeah.
so you plug that in to get g equals v squared over h over 2, and you can rearrange that to v equals root 9.81 times h all divided by 2. Root.
Okay, so you've concerned yourself with this circular part. Now, is there any consideration we have in terms of, or that we could think in terms of the energy that the ball has when that it is released at A,
Yes.
and how that
So
then relates to the energy at the point where it
mgh
comes off?
turns to half mv squared if there's, especially because there's no friction, it would be very 100% efficient. Okay, so the start of the circle. So at the bottom, so at the very bottom,
Yeah.
before it starts going, its velocity will be root 2 gh,
Okay.
because gravitational potential energy is turned into kinetic energy.
Brilliant.
And then your that's your u. So yeah, and then your acceleration will be using the central Peter force equation. So so your a will equal, what's the equation for acceleration in central?
So this here is the acceleration component, v squared over r.
V squared over r.
Yeah, or
Mu
squared r.
mu squared.
Okay.
Okay. And then your it won't be a constant acceleration in that circle though, will it?
As in, will it be undergoing uniform
Will the,
circular motion?
will the acceleration be changing during this?
Yeah, well, let's just think about that question. And would the acceleration be changing?
Yeah, no, we're not. Yeah, will it be changing during?
It would be, wouldn't it? Because I think at different points, you've got your components of weight, or mg,
Yeah, yeah. So you
will
can't.
be slightly different, won't they?
So you can't use
Yeah.
do that for that. So yeah, so then you make the mg equal to mv squared, and your v equals to root g. Would your V be 4?
4. Yeah, so let's just think about what you've possibly done so far. So you've thought about the energy we started off here with,
Yeah.
which is mgh. Yeah, good. And we're saying, well, it's going to come off somewhere. but it
I'm
definitely will not-
saying it comes off when the mg is greater than mv squared over r.
than mv squared over r. Okay. So is there any way then we can equate? So you've said when mg greater than
Yeah,
mv squared over r,
when the weight is greater than the centripetal
where this is
force.
h over 2.
And then your V, can you plug in from what we've calculated before?
Yeah,
Of V equals root 2GH.
I see. Okay, I see exactly where you've come from. But to just break the problem down a little bit more, because I think there's some other salient points here that we need to consider if we are
Okay.
going to look at this from an energy point of view. Okay, so just as a way of thinking about the problem, firstly, the ball won't come off at this highest point. Yeah. Have you encountered something known as loop the loop maybe in your studies? Loop the loop to work out what the height would have to be for, say, something that's rolling in a circle for it to actually make the loop. Okay, not to worry, not that it's very important at this stage, but we can just think about this or break down the problem and say, okay, it's going to come off at some point. We could call it there. And in relation to the horizontal axis, we could say it's at an angle theta where it comes off.
Okay.
We don't know where it is, but the maths, hopefully, by using an energy balance, will work things out for us. Okay, so if we think about the forces acting on this body, what forces would you say are acting at the point where it just comes off?
Gravity.
Yeah, absolutely. So I've got mg.
Mg.
Yeah, and what else would we say?
This, we say this the center of the circle as well.
Yeah, so that's the centripetal force here acting, if you like. But as you said, you're saying when gravity is greater than mv squared over r, it will come off. So that's one way, and I know exactly where you've come from. Is that because you're considering that the reaction force is not there anymore present? Yeah.
Yeah, because didn't it say the friction is negligible?
Yeah, absolutely. Friction is negligible, but we still have a normal reaction force as this goes around, because at any point in time there's a reaction force acting because it's pressing against
Yeah.
the inside. Yeah. So the point where it comes off, that reaction force must be 0. So if we think about an energy balance, if you like, at this point, we're saying the energy we start off is mgh, and this must be equal to the energy we have at the point where we come off. Now this is going to be h over 2 sine theta.
Okay.
And take that height, wouldn't it?
Yeah.
So that will be h over 2 sine theta. So it would be mg multiplied by h over 2 sine theta, plus it would have half mv squared component, which is the kinetic energy.
Yes.
Yeah. Is there a way you might think about progressing with those two equations?
Well, I'm just going to cancel the n's at the start.
It's a good start.
Easiest thing to do. And then times it all by 2. Let's give 2gh sine theta plus v squared. And then two GH minus G. Okay. Now I need to figure out how to get this height and the angle.
Yeah, so now you have an expression for v squared.
Yeah, I've got GH brackets 2 minus sine theta.
2 minus sine theta. So did you obtain that then by multiplying everything by 2?
Yeah.
Okay.
Multiplying by 2.
So this would be 2GH. This would be H sine theta.
GH sine theta.
Thank you. And then this would be your V squared. Yeah. So your 2GH, GH is out there, and you've got 2 minus sine theta. Okay. So what next can we do now? Remember, we can think about this in terms of forces now, can't we?
Okay.
So if we think about the forces acting on this body at this point, what would you say the component of the weight is acting in that direction towards the center of the circle? What would the component of this weight be?
0. When's it?
So let's just draw the, so that's the object,
Yeah.
the weight. This here is theta.
So you'd say that weight is equal to what's let me get my trigonometry now.
Yep.
You say sine theta times
Yeah.
the centripetal force is equal to the weight.
You could do it that way. You could absolutely do it that way if you want to look at it in terms of this way, or you could resolve this weight and make it act along this direction where the centripetal force is acting.
Yeah.
And sometimes it's easier depending on which axis you decide to resolve in. But if we decided to resolve along that plane, what would our expression then look like if we're resolving in the direction of the centripetal force?
Okay. Your weight would be divided by sine theta. Would
Sine
be,
theta.
yeah.
So if I draw a 90-degree angle here, so this angle here, so let's imagine this is 90 degrees.
Yeah.
So this here would be 90 minus theta. And this angle here would be theta. So if we want to work out this component of the weight acting along this direction, would you agree that I must say mg sine theta?
Yeah.
Are you happy?
Yeah.
Good. So we've got mg sine theta, and this must equal what? That must equal the centripetal force, correct? Because at the point where it leaves, there's no reaction force.
Yeah.
Because otherwise we'd have had an expression saying mg sine theta plus n must equal mv squared over r, where r, of course, is h over 2. But this n, the normal reaction force, is 0 because it's just come off. So far, so good?
Yep. So far, so good.
Okay, and how can you proceed from there?
Okay. And then now you can know what your sine theta equals.
Good, well done.
So your sine theta equals 2v squared over hg.
Okay.
And then you can plug that back into your energy equation at the start.
Yeah.
So get v squared equals gh 2 minus 2v squared over hg squared 2 gh minus 2v squared. So 3v squared equals 2gh Is there a way to get rid of your height? No, no,
Uh,
no.
so the angle it comes off will most likely be dependent on the height,
Yeah.
because it will
Okay.
depend on how much energy is in it. Yeah. So
Yeah.
it will
So
depend on the height, but will not necessarily depend on the mass.
I've got your V equals √2/3 GH.
Root 2 GH over 3. Well done. And you got there. Okay, good.
Yeah.
Okay, excellent. So we're going to look at some curve sketching then. Is that something that you've done whilst at school, practice that?
Yeah, we've done curve sketching.
You've done some curve sketching. Okay, good stuff. So let's just have a go at, I'll just pick one, leave that one for now. So we'll go at sketching this detailed graph of log to the base x of 2.
Okay. Okay, I'm gonna probably plug just straight away, just giving myself some easiness, some numbers, and just some integers into the equation. So you know when your x equals 2, that your y must be 1.
Okay.
That's what I'm going to start at. And you know when your x equals 4, your y equals a half.
Okay.
And then when your x equals 8, your y equals a third. So you're going to get some sort of exponential curve with that will be so. And then when your x is 16, your y will be a quarter, and then when it's 20, no, when it's 32, then it'll be a fifth.
Okay.
And then so on, and then but then no, it won't be an okay. It won't be an exponential at all. I was capping, you know. Will it sort of be like a mountain, like a lot of mountain thing like this?
Okay. Have we got a little bit of a shape there? So you looked at some different points.
Okay, this might be a bit. I definitely know from one what it's going to look like.
Okay.
When it's 0, what's it got? looking at that. Okay. Okay, this is, I'll just get what I've done
Okay.
because that's going to be that way.
Okay, good. So you've got that first in that first quadrant. Yeah, all right. Are there any asymptotes of any sorts?
Yes, there will be because you can't, something to the power of 0 cannot equal 2. So you can't. Um, you can't have any x values being minus either, can you?
So we'll be looking at the positive domain, so to speak. Yeah,
Yeah.
good.
So okay, and then is it something like, okay? I think with an asymptote for y equal, because you can't have y equaling 0. So
Okay, I'll stop you there, and we'll just try and think about it. So what have you got so far, just to give me a bit of
something
a
like,
glimpse? Something like that. Okay, so you've got a shape for one part where x is increasing. Okay, and you seem to have the general shape. I think it's what's happening towards closer to x being 0 that we probably need to look a little bit further there. Is there another more, I suppose, an elegant way you could approach it by thinking about it in terms of curve transformations?
could you think about like differentiating it maybe or something like that? I don't really know.
Yeah, that might help, but it might still be problematic because we've got a log to the
Yeah.
base x. But we could think of a base change. Is that something you have done before? Base change.
I don't think so.
Okay. So if I have something that is log to the base of A of B, this can also be expressed as log to the base of C of B over log to the base of C of A. Seen anything like this before?
I don't think so, no, but
Okay.
I think I've read. I haven't used that before. I think I've read something about something like it.
Something like that. Okay. So we can also have a special case where log in the base of A of B can also be thought of as log to the base of B of B and log to the base of B of A. A log to the base of B will of course be 1. So this is one way of transforming a log or changing the base of a log.
Okay.
Okay, so we could apply that law to this case.
Okay. Yeah, so then you
And what
have
would that give us?
y over log 2 to the x.
Is that what you have? I hear you have.
Yeah.
Good. Now can we manipulate or think of drawing a curve for that function?
So when that okay, so y okay, okay. I think I got it now.
Good.
Okay.
Okay. Avenir is still there and much better than the first one. I'm absolutely getting. So is that an asymptote? The
Yeah.
okay, and where does that asymptote fall? What value of x?
X equals a half.
X equals a half.
Yeah.
Yeah. Okay, so let's just break this down together. So if we had to look at the sketch of, let's just sketch this function, log to the base 2 of x. What does this look like? Log to the base 2 of x.
Log to the base. These I rearranged it to log 2x equals y to the power minus 1.
Yeah. Or in other words, it is if we think about the so which one is it again? Sorry. So you can say log. So we want to sketch this graph here, don't we?
Yeah.
Yeah. And so this is now looks like 2 to the power of y equals x.
2 to the power of y to the power minus 1, isn't it?
So 2 to the power of
Y. It's log 2x equals y to the power of minus 1.
y to the power y. Should we say y to the power of minus 1? Are you trying to equate it to this, you mean?
Yeah, are we equating it to that or?
Oh no, this is so this is not so this is let's just call this z.
Okay, yeah.
Makes life much easier. So now
Yeah.
we've got 2 to the power of z equals x. So this is a bit like plotting an inverse almost, isn't it? So plotting the inverse of this 2 to the x. So if so that would be a reflection in the line y equals to x of the function 2 to the power of x, wouldn't it?
Yeah. 310. I haven't done this in a while.
Good. Okay, so that would be, sorry, 0, 1.
0, yeah.
So on the other side, it's now going to fall on 1, 0.
Yeah.
Okay. Now we can see if we use this function here and plug it back in there.
Yeah.
So log to the base 2 of x at x equals to 1 gives us a 0, doesn't it? So we're going to have a 0 input, in which case that must be an asymptote. You happy with that?
Yeah.
Good. Now we can see that as this increases, as the y increases to infinity, well, what should happen at that point? The values should get smaller because we've obviously got a bigger denominator. So would you agree that it should look something like this? So
no, did I say the asymptote was at x equals a half and x equals 1? Yeah, I don't know why I said that.
Yeah, but so you got your x equals to 1 then. Fantastic.
Yeah, I don't know. Yeah, sorry.
Not a problem. And how would it look then on this side of things? Well, we can see that the y is approaching negative infinity.
Yeah.
Which means that if I'm dividing here by infinity, essentially, I've got a 0 term. So it would start from there. So I'm using this part of the graph now. So it would look something like
I went the wrong way.
Yeah, but you got there though. I think you've seen the rationale behind it.
Yeah.
Yeah. And I think this is where you had some of your points you mentioned before, where when x is 2, you had the 1, and so you had this part of the curve. And I think it was just here and working out the asymptote. And I suppose by inspection, you could have possibly ascertained using the method that you were going down that at x equals to 1, you would need an asymptote.
Yeah.
Because you would not find any number or 1 to the power of y, which would equate to 2.
No.
Yeah. Okay. Good stuff. So that was good. I will. I think you could definitely do with a little bit more practicing on some of the curves. By the way, I'm now just giving some feedback, so we're outside of problem solving mode. So that's the reason. So there's no harm in. I can send you a few more questions, Isaac, just for you to have a go at and build some confidence. Okay. And just also think about transformations at times. I've also got just a few notes just to kind of give you some feedback and just on sort of approaching curve sketching. I was hoping we might get some time to probably look at some type of statistic type problems, but not sure. How do you feel in terms of your core strengths? Where do you feel your greatest strengths are in mathematics? Let's not say strength, weaknesses, because it's yeah, weaknesses makes more sense.
My stats is probably I'd probably say some of the pure parts, like not because I don't understand some of the lessons, because we had a different teacher that I didn't suit his teaching style as well. So I'm catching back up on that. So that I would say, and that we did proof by induction. I don't need to definitely go over. Curve sketching, and the Maclaurin series. Those are probably my
some areas that you need to cover. And of course, the thing is, they would understand as well. You have not finished the entire course, A-level course, but also what you want to demonstrate is that you've been able to go the extra mile outside of your lessons, if it means to try and consolidate any areas that you find a bit challenging, so to speak. So just some feedback then, and I will send you this video as well, Isaac, so you can be able to see and also reflect as well, because I think it's quite important to reflect after such a long session. And well done, because obviously, you've had a long day. No way are you going to be interviewed so late, and so your brain may not have been firing at full throttle. I absolutely understand. Okay, and of course you still have, you had a full school day today, didn't you?
Yeah, and a double swim session. So
Yeah,
swim in the morning, swim in the night as well.
Oh, you're swimming as well in the morning.
Yeah.
That is intense. That is very, very intense.
On the 13th, that's definitely not happening.
Right. Okay, good. But the key thing is what they look for as well is if you're a rounded student, as from reading your personal statement, you seem very rounded. You seem like you like to push yourself in everything that you do. That motivation. It's not just so you're a person who shows passion, who's got passion for whatever you're doing, and that passion is coming through. What I want to give you is just some pointers, especially on the day, because you will undoubtedly face problems, questions in novel situations, and I'm hoping that some of the problems that we went through today are things that maybe kind of give you a different way of looking at things, because they're not your typical A-level problems, so to speak. I don't think that you'd have been going through questions like that.
No. Yeah, they remind me a lot of like the maths challenge and stuff like that, sort of things.
Yeah. So there's a little bit of there's a bit of an element in there. Good. And so you've got some exposure to that as well. Now, what I would strongly suggest is when a question is posed, just posing a little bit, because I could see that you were very quick to go into responding to the question. And when you pose a little bit, and by this I mean not a long 30-second pose, because you've only got a limited amount of time, but even a 5-second, and I know it'll seem like ages, or even 3 seconds if you think that's a long time, but just that minor delay in before you start speaking shows a maturity, in the sense of you're taking time to really check if you've understood the question, and you're also giving your brain time to start processing how it can approach that problem. That's the beauty about it. And also, not all the time, but as often as you can, when a question is asked, sometimes it's also good, especially when it's those really kind of complex questions where you're going, where do I go with this one, type of thing. Yeah, to give your brain a little bit more time as well, so you can gather your thoughts. It's quite an intense interview in itself. Ask the interviewer, okay, so do you mean this? Or like, try and really find out whether you have understood the question. There's no harm in doing that, okay? Because sometimes what tends to happen in such a high pressure environment, you might end up thinking, right, I think I know where I need to go with the question, but you may not exactly have answered the question or gone the right route. Okay.
Like in tests, I don't know, it kind of feels a bit like, it feels like it's weird doing an exam when you can ask questions, sort of thing. Because all that,
yes, you've absolutely got it. On a positive part, you seem to be working well with hints. Yeah, so when you realize your solution is not quite going in the right direction, you're given a hint, you seem to then pick it up and try and build from there, and that's really, really good. So what I saw is that you went regularly asking for hints, and that is something they're going to want to see. They really want to see how you approach a situation. So most of the time they will also want to see your originality in thinking. So they know you will get stuck, but they will give you hints, and then try and work with those hints. But from what I saw today, you were really good in terms of that interaction.
Did you say not to ask? Did you say
no? I say so once you're given a hint, try and work with it. So what I'm trying to say is as opposed to asking for so many hints, sort of hint after hint after hint. So once given a hint, try and work with that hint, and really explore what they're trying to say, and try and work with it. Try and be creative with it. You may not necessarily end at the right answer solution, but at least they'll see that they gave you something, and you took that that self-directed move to try and build on it, as opposed to wanting to support it. Because one of the things, or the nature of Cambridge, is that even the lectures themselves, what they give you is very much a skeletal frame. So they don't spoon feed you. And what they'll be expecting is that you're going to do a lot of, once you're given that framework, you're going to build up on it. And essentially what they're expecting of a reader of mathematics is that you're not going to have, so to speak, a ceiling to yourself. You're going to blossom. You're going to grow and develop without, it's not like at A level where you've got a spec. You're going to go beyond the spec, so to speak. And that's what they're trying to see as well when they're giving you hints. What can you do with them, so to speak? Yeah. So that's something that I saw that, you demonstrated. So that's a key strength, more on a positive there. The other thing as well, I notice as well is try and vocalize a little bit more when you're working through problems. Something I think you could definitely improve on. So vocalizing a little bit more.
If I was like, when you just like a lot of thoughts are going through your head.
Yeah.
I didn't know what, because some of them, sometimes I have thoughts that I know that will not work, and I just do it in my head just to make sure.
Yeah.
Is it still worth talking about those?
Good point. Very, very good question. And that happens, even to me myself when I'm working through problems. I do work through problems code, and I like to work through problems code in front of students because I do also like them to see me struggle. Yeah. Because they've got this impression to say, okay, Cambridge graduate, so he's not going to find any. So it's also good for them to see you struggle when you've got a really hard question, and to almost for them to hear my thinking. Okay. And sometimes I don't always say the most sensible things, or don't always think of the easiest ways around things. But the good thing is that in vocalizing it, one thing is it serves two purposes. One is obviously to show the interviewer your thought process, but the other one is for you, it gives you a form of, it's like a feedback loop. So you hear yourself, and you can, because it's a sound you're hearing, as opposed to just in your head, you can quickly work out whether it makes sense or not. Yeah. So it's also helping you. So that's that part. And there are times when it's not wrong to have 30 seconds of silence while you're working through it and say, let me think through this. And while you're thinking about it, really kind of, okay, if I think of going down that route which involves using an exponential, what could potentially be the problem with that? Maybe let me try put it on paper. So I'm just giving a bit of a scenario. You've thought about something, but you're thinking it might not quite work, but then you think, okay, I'm going to give myself a chance to see what it looks like on paper. And you go, oh, hang on, actually, I've just thought of something else to try. There's absolutely nothing wrong with that. And oftentimes is even what you think may be a silly thought or an idea may just give a glimpse to the interviewers to say, okay, so he's actually got quite a synoptic way of looking at a problem. He just doesn't look at it in a kind of one-track fashion. While he's solving it live, his brain is still processing as to, can there be other ways I could look at this? Which is an all right thing. It's an absolutely all right thing. Okay. On the part where, yes. So on the part where we were just kind of gauging your interest in mathematics, you definitely spoke about it with passion. And if you ask the question such as, you can be asked any question, but if you ask the question where you need to maybe talk about an experience that is a bit personal, or when I say personal by that, I mean something that relates to an aspect about mathematics you love and how you would relate or go on to show how you're passionate about it. Try and, I don't want to say, I'm not trying to say necessarily, well, I'm almost, yeah, actually, try and think about ways of being succinct.
What was that word?
Succinct. So succinct. So as in, try and get your message across with few words, your main message you want to send across. Yeah. And then, because sometimes, depending on the interviewer, sometimes this happens in your interviews and it can be very disconcerting. I hope it doesn't happen to you, Isaac, but if it does, I want you to keep a cool head. And sometimes this is what happens. You will be talking through something and then the interviewer may go, no, that's it, that's enough. And you go, ooh, was I saying the wrong thing? And they then move on to the next problem. And as you're working through that problem, they may just say, yeah, that's enough, and then move on to. Now, under that pressure, you may think, I didn't do something right here, because there's some interviews whose emotions you can't easily read.
Okay.
The interviewers whose emotions you can read are really good, and you're going to, you know, there's some interviewers who will literally, as you're working through, they'll be acknowledging, nodding, and giving you the, you know, yes, that's it, absolutely good. Similar to what I was doing. Yeah, you're right. Yeah, okay, let's think. So you will have some like that, and then you've got some who's, like I say, emotions very hard to read. They'll not give you a lot of cues.
Okay.
Okay. Now, in that scenario, don't panic, because it's very easy to panic, especially like I said, when you're feeling like your trend of thought is being interrupted, which sometimes does happen. And what that can mean, and oftentimes it means that they're looking for a particular skill for you to demonstrate, and you've demonstrated it, and they don't need any more evidence of that. So don't take it.
Good thing.
Sorry?
Is it something? It can be a good thing if they
Yes, exactly.
Okay.
But if you don't know it and it happens to you in an interview, that can
Yeah.
really unsettle.
Your mind can wander anywhere to what. Yeah.
Yes, that's just really going to unsettle you. So just something to bear in mind. Okay. But once you've done a little bit of research, which I know you're going to do, you're going to have a better idea of which areas, of course, the interviewers are working in. Another thing you may be asked at the end, you may be asked, do you have any questions for us? So have you thought about how you'd respond to something like that?
Would you ask a personal question, or would you ask a maths question? I don't know. I don't know. I haven't thought about it.
Yeah. And it's good to think about all these things, because on the day, if you've thought about all these things, it will show, and you know that level of preparedness will only work in your favor. And again, it's worth gauging the sort of rapport you've built. But you Isaac, you come across as easy to talk to, and also you come across as somebody who can get relaxed quite quickly, which is very important. Okay, because it's the first time we've met today, and you are relaxed, and that's very, very important. Okay, the more relaxed you are, the better, because also for your nerves, it helps the thinking. You know, and it will also help you to string words together, because the last thing, and this does happen again during interview, people get so nervous and they can hardly string two words together. And, you know, a question where you ask like, you know, what equation do you show your aunt, becomes a really, really hard question because of the nerves in the interview. So, you know, that's really good. That level of maturity is coming through. The one thing I would like to say maybe as well, which is, so when you asked why you'd like to come to Cambridge, it wouldn't carry a lot of weight if you mentioned things to say, you know, like your dad lives there and such, so that you may want to edit out and maybe try and think of other things, maybe, you know, like how you spoke about the PhD student who motivated you, and also the fact that, you know, you want to be in an environment where obviously it's challenging you, because you like to challenge yourself, both physically, but also mentally. And, you know, the thing that you have said is you are interested in sport. So you could also use that, because they've also got, you know, there's Emmanuel have got, you know, a very strong, if you like, focus on sports as well, in terms of the intercollegiate side of things, in terms of sporting and competitiveness. That's quite big there as well. So you could use that as well to your advantage. So use some of the things in your personal statements when describing it, because what they also want you to see is how well does your personal statement tally with what you then describe about yourself.
Okay, and when I ask if I'm asked why I want to come to Cambridge, should I talk about something like I really like the maths department, or like then if they've built
or how you know, it's something that shows that you've done a little bit of research about the maths department, in terms of maybe how the course is structured. How does that appeal to you? Yes.
Okay.
And you touched on something about the supervision system, so that was good. It shows that you've done a little bit of research, but you were only on the surface.
Okay.
So you could do a little bit more digging, just to show that you know you've gone that extra layer. to really gauge whether Cambridge is right for you.
Yeah.
Okay. And a minor one, really difficult, really difficult. If you can avoid it, and it's very difficult. If you can avoid it,
is it saying like?
don't try and use like, yes.
Yeah, I knew I was saying that.
Okay.
I clicked, but after the 20 minutes, I was, oh my God, why am I saying like so much?
Okay. Catchphrase. Okay. But you're self-regulating. So if you pause a little bit more as well, there's absolutely no harm. You don't have to feel like you need to, and there I'm using like, you don't have to feel that you need to fill every silent moment with a word. You can literally say a sentence, pause for 5 seconds, even 3 seconds, carry on. And also, if you pause a little bit, it gives them time to probe or ask you a question about something you've just said. So you don't have to kind of go almost in a trained fashion.
Yeah.
Does that make sense?
Yeah, I can't. Yeah, that's. But I can't believe. Yeah, you point that out, because I was like, why? I was literally talking to myself, like, why am I saying like so much?
Okay, so you self-regulated. Okay, good stuff. No, Isaac. So those are sort of the main pointers, and I think you know some of the areas that you need to work on. What I'll do is, I think this might really help you, because there's quite a few really interesting questions that I was hoping we'd cover, but we've covered quite a few here, and there are really some interesting. This is an interesting curve to try and sketch. Where is that?
The one before I've seen, the sine x over x.
Seen that one before?
Not that one. I haven't seen that.
Yeah, that's a really nice one to have a go at. Arcsec x, sine x. Yeah, this is a very popular one as well in physics.
Yeah, it's like
the
YouTube video, Cambridge. It's the first question they ask.
Yeah, good. So they're awesome. You know, there's some really good ones anyway in here. And what I'll do is I'll send over the solutions as well, so that of course you can self-regulate and you can have a look at some of the solutions. And on the solutions as well, I've included detailed working as well, so you can then of course see how to go about it. So it's a little bit of commentary, as it were. Yeah. How did you find that, Isaac?
That was all right. I feel like some of the questions I could have done a bit better on, but I just need to expose myself to enough of them so I feel more comfortable. Because it's a lot in A level. It's a lot of just, oh, I recognize that, I'll plug that into that formula.
Yes.
But it's just a lot more. There's
novel situations, and you have to apply yourself differently by thinking outside the boxes sometimes as well.
Yeah, it's a lot more recognizing different stuff into one big thing.
Correct.
I'm not that used comfortable, but I think I can become comfortable with it.
Yes, and they will be looking for that. But the good thing is, regardless of how it starts, they're going to start you off nice and easy and build you up. They're not going to drop immediately into a very complex calculation. So, you know, that's generally what they will try and do. And if they do drop you at the deep end,
yes,
if they have to then readjust to see where your level is to then bring you back to the question, then they will do that. So that's just something to help you with being relaxed on the day. Okay.
Perfect.
Good stuff. Right. Okay. So I'll send all of this, the board work, I'll send the video, and I'll send solutions to the graphs. So you've now got Friday. Let me know if you wish to squeeze in an hour, but I think in terms of the general feedback, I think you've got enough here to work with. But if you wish, you want to have a final session, we might be able to squeeze that in. But your mom did say, you know, if you think, but I think I've given you enough food for thought, and you need a little bit of time to go and work on those things as well. And then should you wish to have another session, we can possibly try and squeeze that over the weekend. But otherwise, you know, if you feel you've worked enough on the material I'll have sent you, then again, that's absolutely fine. But I'll definitely nonetheless wish you the very best of luck, and I would love to hear from you. You know, just drop me a line once you have once you've calmed down and all the nerves are gone, and you've you've realigned yourself back to normality. So it doesn't have to be on the day, it can be after. All right.
Well, I really appreciate this. Thank you.
You're most welcome, Isaac, and I've got my fingers crossed for you.
Thank
Cheers
you.
again, yeah?
Thank you so much.
You're welcome, and have a
Bye.
good one. Cheers, bye now. Bye.